So I'm going to incorporate the pod key into lecture today because it's a nice segue into lecture. So pod 24 was asking you guys to give me the reaction product or products for this reaction. And yesterday before we left, I said with cyclohexanes, it's really important that when you do the E2 elimination reaction that your leaving group is axial and your beta proton is axial, right? So if we transpose that two-dimensional structure into a chair structure, you can see those beta protons drawn in red are axial and the leaving group's axial, right? This proton over here, even though it's beta, isn't in the correct conformation to be used in that E2 elimination reaction. So if I redraw it, you can see those red protons are dashes and our bromine's going to be a wedge. We only have two beta protons that can be used for this E2 elimination reaction. So let's take a look at these E2 products along with their name. First one, I'm going after that top proton in red. We're going to clamp down and we'll end up forming one methyl cyclohexene. For the bottom reaction, we're going to get that other red proton and we're going to form R3 methyl cyclohexene. A lot of people were asking me, do you need to include cis or trans or E or Z with cyclohexenes? No, it's optional. You can, but you don't have to. Why is that? It's inferred. Can you ever really have trans cyclohexene? No, it would be too energetically unstable. You actually physically can't even build it with a model kit if you tried. So because of that, it's inferred. You don't have to include it unless you absolutely want to. So it's not incorrect if you include it. It's just extra work. And then it's really important to number the correct way too. So with alkenes, remember that the alkene needs to be at the lowest possible number. And if there's a tie, then you want your substituent to be at the lowest possible number too. So in the first one, we want a number going clockwise, not counterclockwise. All right, so now I've got a thought experiment for us to consider. The thought experiment is, which product is the thermodynamic product and why? So I want you guys to talk about this with your neighbor. Which of these two products do you think is going to be your most thermodynamic product and why? And I'm going to redraw them down here just so we have room. Oh.
Yeah, you're right. Yeah, you're right. Sorry. That's what I meant. You knew what I meant.
All right, give me a thumbs up if you guys agree with your partner. All right, looks like a lot of thumbs going up. All right, which one do you think is more stable, the one on the left or the right? Left. All right, this one's thermodynamic product. Why is it our thermodynamic product? Anybody want to share? More substituted alkene, right? We said the more substitution you have coming off of your alkene, the more stable it is, right? So really when it comes down to it, this is our thermodynamic product because this is tri-substituted. And this one is only di-substituted. We know that our tri-substituted product is going to be more stable than our di-substituted product. All right, just to review too, when we say thermodynamic versus kinetic product, what's the difference? Does anybody remember the difference between your thermodynamic product and your kinetic product?
Thermodynamic is activation energy, kinetics is delta G, right? Is that
Both.
Dang it.
All right, so let's do a little bit of review. Thermodynamic product simply means you've got the biggest change in delta G, right? So let's actually draw a little reaction coordinate diagram over here. Really all we're doing is comparing this drop in energy. your thermodynamic product results in the more stable product. What does it mean when it's a kinetic product then?
Jump back over, use the example we had.
Yeah, the kinetic product, we're not concerned with the delta G. We're actually only concerned with activation energy, right? So our kinetic product has the lowest activation energy. Our thermodynamic product just results in you getting to the most stable product regardless of that activation energy. All right, thought question number 2. Do you think the thermodynamic product is always favored? No? Depends on your base. We just said, too, that kinetic products are sometimes favored depending on the activation energy, right? And so let's make a little note of that, and then we'll talk about these guys. Not always. There sometimes is a kinetic product if one reaction has a lower activation energy. This is a really important theme. So it's not 100% certain that we are going to get that more substituted alkene. It depends. And this comes back to these two gentlemen. Guy on the left is Alexander Zaitsev. The guy on the right's August Hoffman. Two handsome fellows with magnificent beards.
As always.
Yeah, as always. And they were the ones that really did the initial studies on alkene formation, right? Zaitsev came up with this theory where he was really adamant at first that anytime you do an elimination reaction, you're going to go form the more substituted alkene. So let's make a little note of that. So anytime you get a more substituted alkene, you call it your Zaitsev product. You don't have to draw their portrait in your notes if you don't want to. Hoffman, on the other hand, said, wait. Sometimes you get the less substituted alkene. And this really depends on that activation energy that you have to overcome, right? So let's take a look at an example of what I mean by this. All right, so for this example, I'm going to take a look at bromine coming off one end, and we'll have a tert-butyl group over here. And I'm going to make this one a wedge. And I'll make this a blue proton. I'll make this one a red proton. And then up here, I'm going to have some CH3s coming off, right? All right, so let's imagine we've got a base. And in this case, let's imagine that we've got a small base. Let's determine what product or products we could get out of this reaction. I'll give you a hint. There's likely more than one. So I'll give you guys a minute to work on this, but let's try to figure out what reaction product or products we could get out of it. And since there's two reactions, I'm just going to redraw it down below so we can compare the two pathways. And that might also be a little bit of a hint for you guys. And then once you think you've got the products, give me a thumbs up. Yep, small base. All right, raise your hand if you think you got one of them. All right, a few of you. So let's try it. One thing I notice is we've got a problem. What's our first problem? At least the way I have it drawn. Yeah, right now we don't have an anticoplanar beta proton. So what I can do is rotate this a little bit. So I'll just do a simple rotation of one of these positions. That's something that a lot of people get hung up on, is forgetting to rotate, because that rotation does depend on the stereochemistry, right? So if we rotate it like this, we could have our hydrogen up here, and I'm just going to abbreviate this TBU, and we'll move our blue proton back. Okay, so if we have our small base, we know this base will come grab this anticoplanar beta proton, clamp down like dominoes, and kick off our bromine, right? So now our final product will still have this blue proton on there. And there we go. So that's one product. Let's do the same thing with our second reaction. Should we go after the blue proton this time, or does it really matter? It would actually give us the exact same product if we went after that blue proton, because if we look at it, it's not cis or trans, it doesn't matter. Okay, but let's try again. Oops, sorry. With this reaction where we've got our small base. But this time we'll go after one of these methyl group protons. That's also beta. And we can clamp down and we can kick off our bromine. So let me actually draw this out. And we've got this blue proton still hanging out, this red proton, and we've got a CH3 here, and we've got a CH2. We don't have to label those necessarily unless you absolutely want to. Let me actually move this C up a little bit. All right, which one's our Zaitsev product? The upper one or the bottom one? Upper one, all right. So let's make a note of that. That's our Zaitsev product, meaning it's more substituted. And this bottom one would be referred to as our Hoffman product. Anytime you use a small base, or a large base for that matter, you might get some mixture of these. But with the small base, which one do you think is going to be favored? Zaitsev, right? And the reason for that is a small base doesn't really care where it grabs that proton from, right? Small base doesn't have a strong preference either way. In this case, it'll tend to favor the more substituted alkene. So let's make a little note of that. So small, unhindered bases favor the more substituted alkene, which is referred to as our Zaitsev product. The reality is you might get a little bit of a mixture though. All right, so if we think about this reaction though, let's go back up and look at it. We said we're going to get a mixture of these two products. Would this reaction be stereospecific, stereoselective, or regioselective? What do you guys think? Regioselective, right? Because up here we just said we made a unequal mixture of constitutional isomers. That means the reaction is regioselective. In this case, we said that this will be our major product, and this will be our minor product. Does that make sense? It means oftentimes these reactions can be rather messy, and you do have to separate these out. The good thing is, because they're constitutional isomers, they have completely different physical properties. That means we can separate them through techniques like distillation, and separate out each component and isolate them and purify them, right? So that's not as hard as separating out a mixture of enantiomers. It's much, much easier. All right, now let's look at example 2. All right, for example 2, we'll do another we'll do this one, where we've got bromine hanging off and a methyl group. Is this chiral? No, there are no stereocenters, right? So in this case, it's an achiral starting material. We've got a leaving group coming off. But in this case, what I want to do is treat this with a strong base. However, this time I want it to be bulky. And just like last time, I want us to consider any possible product that you can get out, and then we'll assess which one will be major and minor. So I'll give you guys a minute to work on this. And then once you think you got it, check with your neighbor too. The other thing I want you guys to pay attention to is, we know that this is our beta position, right? The proton that you're taking from that beta position, I want you to determine whether or not that should be a dash or a wedge. You might want to go back in your notes from the pod too and look at that, or notes from cyclohexene E2 reactions. I'll draw them both in here for good measure. This bromine up. You guys are very quiet today. You can talk with your neighbors.
I know.
I'm pretty sure when it comes to if you're leaving group as a dash, the beta hydrogens will be the worst.
Because that would be that's down.
And then
But because this is
so,
up,
and
this
then
makes
dash.
it dash.
Yeah. So,
And what about the other one?
But-
Up and down.
but this
This one would have been no, it's down, so it would have been up, so it would have been dash. Oh, the hydrogen would have dash. Oh, yeah, that's true.
so formation of bromine is dash. And section behind it's gonna
Is that what you got?
Wait, so I have a bromine, it's a dash. I did look, so I had a bromine, it's a dash.
Now,
Right?
the question is,
I share a flip, it's not a wedge, or not axial. That means I want a axial hydrogen, which means I should flip it up, it should be equatorial.
this one's the major.
So that is one of those, and obviously it's that one. So that's dash.
Okay, it's both.
And this one.
But it's still the side
down.
set. The side set is the major.
So it would have been a dash.
So it's still a side set.
Yeah, you didn't share that.
All right, let's see a show of thumbs. How many of you guys think you got it? A few thumbs? All right, let's do one of them together. So let's do the top one. The question is, am I going to grab this proton in red, or am I going to grab that proton in blue?
Blue.
Ooh. Some disagreement. So remember, they have to be on opposite sides, right? So the blue proton, or the one being pointed to with the blue arrow, is on opposite sides of that leaving group, so that would be the better pathway, right? You don't want your leaving group and that beta proton to be on the same plane of your cyclohexane ring. They have to be on opposite sides. So let's go ahead and correct that, and we'll say, all right, we're going to grab this proton, we're going to clamp down, we're going to kick off that bromine. Does it matter which side I take the proton from? No, because it would give you the exact same product. All right, so let's go ahead and draw the product that we get out now. Oh, that looks like our problem of the day product. Let's do our other reaction. In this case, we could say, you know, these protons are also beta. Clamp down and kick off our bromine.
Did we lose that wedge or we just...
That's a good question. So are you saying, did we lose the wedge up here?
Yeah.
Does it matter?
That's what I like to know.
yeah.
What's the hybridization of that carbon? SP2. So it's trigonal planar. We don't have to use dashes or wedges, which is pretty nice, actually. All right. So if we look at this, we've got two possible products. The one on top, is that our Zaitsev product or our Hoffman product? It'd be our Zaitsev, because that's our more substituted alkene. However, the one on our bottom is going to be our Hoffman product. Oop. That's our less substituted alkene. All right, the question is which one's going to be major and which one's going to be minor? Yeah, we're probably anticipating that it's going to be flipped. But now we have to imagine ourselves as this big, bulky base, right? If you're a big, bulky base carrying around a bunch of carbon chains attached to you, you're going to have a harder time going after the proton shown in the blue pathway than the red pathway, right? Because in the blue pathway, you have to orient yourself at the correct face of that cyclohexane ring, versus the red pathway, you're just going after a methyl group that's essentially spinning around like a helicopter blade. You don't have to approach it from a specific angle like you would with the blue pathway. So whenever you have a bulky base, you tend to favor your Hoffman products. So in this reaction, this would be our major, and this would be our minor product. So let's make a note of that too. So up here we said small unhindered bases favor the more substituted alkene. Big bulky bases favor the less substituted alkene. Which is our Hoffman product. All right, and let's, yeah.
Does it matter which one of those Hoffman, does it matter which proton go off, or does it not really matter for that one?
For that one, it doesn't really matter, but it still should be anti-coplanar. However, with the methyl group, we know it can spin around like a helicopter blade, so it could be any of those 3 protons. Yeah. So big bulky bases favor the less substituted alkene, and the reason for this is when a big bulky base is used, the Hoffman product is the kinetic product. Meaning it has the lower activation energy. It is easier to pluck, that's the science term, a proton off of a less substituted carbon. It's a little abstract to think about, but Hoffman products typically aren't seen in a major quantity unless you're using a really, really big bulky base that has a hard time going after some of the protons in your molecule. By doing that, you're changing the activation energy for that deprotonation. All right, so let's come up with a good list of some big bulky bases that might be useful for favoring the Hoffman product. All right, does anybody have one that they want to share? Yeah, we talked about one already. Potassium terbutoxide is super duper common. People will oftentimes refer to this as KOTBU. So TBU stands for terbutoxide, or TBUOK, or KOCCH33. These are all the exact same thing, right? So you might see it written a few different ways. It's all potassium terbutoxide. Another one that you might occasionally see is the analog to this, where it's got even more gunk hanging off of it. This is super duper bulky. Which one do you think is going to result in more of your Hoffman product? The terbutoxide or the other one? The bigger one, right? So you can even amp it up to be a bigger and bigger base, and that can favor more of your Hoffman product. Usually in your textbook, though, you'll see potassium terbutoxide because that other base just isn't commonly used. All right, the one last one that is more common in a research setting. Whoa. Let me actually fix this. Does anybody remember what this base is called? It was on our common base handout. It's lithium, and then we've got these groups. What are they called? isopropyls. We've got two of them, so it'd be lithium diisopropyl amine. Yeah, so this is often referred to as LDA. LDA is a really nice base because you've got these two giant isopropyl groups dangling off of it, which means it has a hard time fitting into those small corners to get those protons coming off of the more substituted carbon. So anytime you're shooting for a Hoffman product, try to always use one of the more bulky bases. Does that make sense? All right, there's one last thing I want to talk about with E2, and then we'll do some practice problems. And that's the rate of E2 reactions. So let's consider a couple of reactions here. Let's say I've got this reaction where I've got some hydrogens coming off this end, and then hydrogens over here. What I want you guys to do is to do this E2 reaction, but let's draw the transition state before we get to our final product for this reaction.
We're not told if it's a big base or small base.
Yeah, in this case, it doesn't really matter because we only have one type of beta proton to go after. Right? So it could be a big base, it could be a small base, it only has one option. So in this case, we could say, right, it's going after this, it's clamping down, it's kicking off our bromine, but let's draw the hybrid transition state with the dash bonds, showing those bonds being made and broken. And I'll get us started here too. I'll do my dash bonds in red. And we're kind of approaching that trigonal planar geometry, so I'm going to try to represent that a little bit as best I can. And we're also forming the bond between our base. All right, so now let's fill in our partial charges, right? So this base is partial negative, and this bromine's partial negative, and that hydrogen's essentially getting handed off between that carbon and the base, and the bromine's halfway from being lost, and we're halfway between forming that pi bond, right? So do you guys remember transition states? All right, now let's compare this transition state to another example. But in this example, we're going to have a bunch of methyl groups coming off. Okay, again, it doesn't really matter too much what base we use, but in this case, we want to use a small base so we don't accidentally deprotonate one of those methyl groups. So I'll just put small. And we can do the same sort of reaction, but let's draw our transition state just like we did up above. Sorry, I know this is a lot of drawing, but hopefully it'll make sense. All All right, so this bromine's falling off, this pi bond's being formed, this hydrogen's being pulled off, and this bromine's grabbing it. Or sorry, not bromine, the base. And we've got these partial charges, right? Question is, which transition state is more stable? So let's talk about this with your neighbor and see if you guys agree with which transition state will be more stable. And sorry, this should also be a CH3 right here, not a hydrogen.
It's on its way. So that would still be
I'm gonna say the bottom one. I'm gonna say the bottom.
That's not good. Wait, no,
You got the methyl just like high product conjugation.
Kinetic Product has a lower.
I think it's the bottom one. The hydrogen. Lower the hydrogen. The charge is made in the transition state. Because there's no line to charge. You go to Walmart, and there's like 20 registers. There's like 20 registers.
All right, how many of you guys agree? Let's get a list of, or a show of thumbs. Some sideways thumbs. All right, let's stop and think about it though. With the transition state, we're making that pi bond. What stabilizes pi bonds? Hyperconjugation, right? So the more substitution you have coming off of your pi bond, whether it's halfway made or fully made, will stabilize it, right? So if we think about it in that regard, which one will be more stable? Bottom one. So in this case, let's make a little list of that. It's got a more stable transition state, and this one's a less stable transition state. And that means that typically the more substitution you have coming off of your alpha beta position, the faster the rate will be, because that activation energy is actually a little bit smaller. That hump you have to overcome will be smaller in energy. So let's make a general list. Typically, what you do is you'd say, all right, this bromine right here would be the slowest towards E2 reaction. Oh, sorry. Let me move this over. I need more room. This bromine over here, because it's di-substituted now, would be a little bit faster. It would have more substitution when you'd be forming that pi bond. And this would be faster than, or slower than the tert-butyl one. So in general, increasing substitution on alpha or beta positions will increase the rate of reaction. Which is a little bit weird, because with SN2 we actually said the more stuff you had hanging off, the slower it would be, where with E2 it's the opposite. The more substitution you have coming off of your electrophile or the position where the leaving group's attached, the faster that reaction will be. So this is kind of a weird deviation from the SN2 priority list. Does that make sense? All right, what I think we'll do with our remaining few minutes is go through some practice problems. And then when we come in Monday, we'll do a little bit of just broad overview of E2 chemistry and some more practice too if we have a little bit of time. All right, so what I want you guys to do is to help predict the major and minor products for each of the following E2 reactions. And I would just start with reaction A and try to work through it with a partner. And then what I'll do is I'll let you guys work through this for a while, and I'll post the key in the notebook later today so you can check your work. This is also found in your textbook too. It's problem 822. So I'll give you guys a minute to work on this. Or the rest of the period, I should say. Did you guys already do it? Oh, shoot.